A very good evening to all of you who are in India, and good morning to those who may be attending from USA, and a good afternoon to those who may be in Europe. Um, to all the participants, uh, I would like to mention that this is our 17th webinar, and we have had excellent 16 webinars in the past, and every Saturday we have had some program or the other. I'm Ashok Misra, the president of the IIT Alumni Center, Bengaluru. We established ourselves a few years back to be the nodal agency, to be the nodal uh, society to link the IIT's expertise with the industry and the user agencies. Today, we are proud to say that 16 of the IITs, or the so-called first generation and second generation IITs, are our partners, and we work very closely with them and with the industry that we are in touch with. With this in view, we held a very successful IIT industry conclave in February, and our report is ready, and all the deliberations that we had are available on the YouTube channel of IIT Alumni Center, Bengaluru. We'll be putting out the report very, very shortly. We launched this webinar series. In fact, we were planning to take our IIT industry conclave deliberations forward, but the lockdown delayed us. So we thought of starting this webinar series. And these webinar series, as I said, have been going on very successfully. And we are very happy to have this webinar series, the 17th one, which will be on India into the new space age, opportunities and challenges. I have immense pleasure to introduce today's speaker, Dr. K. Radhakrishnan. He was the chairman of the Space Commission and secretary of the Department of Space and chairman of ISRO from 2009 to 2014. He provided a strong and successful leadership to a team of 16,000 plus of ISRO for 37 space missions, including several historic feats in India's space endeavors. Most notably, he is credited for steering India's first planetary exploration Mangalyaan mission to Mars from concept to fruition within a short span of 4 years, establishing India as the first country to have successful mission to Mars in its very first attempt and at a significantly lower cost. You'll be happy to know that a movie has been made, if those of you haven't seen it, called Mission Mangalyaan, and I would say it is a must-watch movie. He has been an astute institution builder with a strategic vision, an able administrator, a dynamic manager, and an inspiring leader, credited with nurturing leadership in the younger generation, especially at ISRO. Dr. Radhakrishnan is a fellow of Indian National Academy of Engineering, National Academy of Science, India, member of the International Academy of Astronautics, an honorary member of UAE Space Agency's International Advisory Board, and a member of the Advisory Council of Sri Pranab Mukherjee Foundation and many, many more professional bodies. Actually, both Professor Radhakrishnan and Professor Dr. Kota Harinarayan don't need any introduction to the aerospace community, but it's my pleasure to introduce them. Currently, Dr. Radhakrishnan is the Honorary Distinguished Advisor in the Department of Space, the Chairman Board of Governors of IIT Kanpur, and the Chairman of the Standing Committee of the IIT Council. He was bestowed with Padma Bhushan by the Government of India in 2014. The Alan Emil Memorial Award of IAF and many, many more awards, approximately 50 of them with accolades. Nature named him among the 10 most important people who mattered in the year 2014. He's an alumnus of IIT Kharagpur and IIM Bangalore. In addition to his technical skills and administrative skills, he's an accomplished Kathakali artist and a Carnatic music vocalist. Now I have delight in introducing our moderator, whom I have known for many, many years, Dr. Kota Harinarayan. He did his PhD from IIT Bombay, and I know him from those days. He is an acclaimed aircraft designer. In his illustrious career of almost 5 decades, he has held responsible positions covering the entire gamut of aircraft life cycle. His experience includes upgradation of fighter airplanes, integration of new weapons, certification ab initio design of supersonic fighters, transport aircraft, and technologically challenging aeronautical programs. As Program Director and Chief Designer of India's Light Combat Aircraft, then known as the LCA, he successfully directed the project to develop first of its kind aerospace ecosystem in the country. India now boasts of developing a state-of-the-art, high-technology, world-class fighter aircraft known as Tejas. I had the privilege of seeing the second test flight of Tejas thanks to Dr. Kota. He was the Vice Chancellor of Hyderabad Central University, visiting professor at ISC Bangalore, IIT Bombay, and the D.S. Kothari DRDO Chair Professor at the Aeronautical Development Agency. Currently, he is the SERB Distinguished Fellow at the National Aeronautical Labs and Chairman of Design Division of the Aeronautical Society of India. He is one of the founders of General Aeronautics, a startup incubated at the ISC Bangalore. He was honored with Padma Bhushan by Government of India in 2002. So participants, ladies and gentlemen, we have two absolute stalwarts in the area of aerospace in the country, and we couldn't ask for a better panel. So over to you, Dr. Radhakrishnan, for your presentation, and Dr. Kota to moderate. Thank you.
Good evening to all of you. Admired moderator, Dr. Kota, Professor Ashok Mishra, Dr. Sushila, and Ashok Kamath, and all the distinguished participants. It has been a great privilege for me to be associated with the IIT system for the last 2 years, and also interact with the IIT alumni community through the IITACB Bangalore. In today's talk, I will cover India into the new space age, opportunities and challenges. Essentially, I propose to do this in 2 parts. First, talking about India's strides in space, and dwell a bit on the space applications in India, and then come to the global space sector and the dawn of the new space age. You could have a few questions taken at that time. The second part, I talk about the opportunities, the 5 E's of the new space age, and highlight on one specific item, that is India's new frontier into the space exploration with the human in loop and with robotics. Can I have the first slide of the presentation? Ashok? Yeah. 1950s, the world talked about dawn of the space age. And India was a new entrant, a startup in those days, an early entrant into this space age. That was 1962. And we started with experiments using small rockets. But the vision was, there is an excitement of doing space science, but there is also a responsibility of making use of this medium for the benefit of the common man, the society. And that was the guiding, indomitable vision of the founder. And then came a set of programs which were chiseled a few considerations. how that is going to be relevant for the country, and what is to be our focus. Self-reliance is quite important if we have to stand on our legs for the space program, which essentially looks at applications required for this country. And we also from the beginning went with the philosophy of team excellence. And in space, especially in rocket science, which is risky and failures are common and we learn from failures. So how the organization could become resilient to the failures that we go through. And this has guided the last few decades of the space program. We started with sounding rockets. They were projectiles. But soon, in the 1970s, we started looking at satellites to be orbited around Earth. Satellites around there to be used for certain applications and the way to build those satellites. This was Earth-oriented space program. And if you look at the communication scenario, the INSAT one was the beginning of the Indian National Satellite System in the year 1983. And now we have come to a generation of the high throughput satellites, GSAT-11, which was orbited in 2018. This has been a long way as we have put a lot of dots there. The frequencies that we dealt with enhanced from C-band to from extended C-band, S-band. Now we are in KU band, KA band. Somewhere in 2005, we got into very high power satellites for DTH services. And we are moving ahead. And if you look at GSAT-11, where are we in the world scenario? GSAT-11 high throughput satellites could give about 15 gigabit per second data rate. And the next one, GSAT-20, would enhance it to about 30 plus. And the world is today at about 100 gigabit per second, high power, heavy communication satellites. That's the direction in which we are moving. Technology is changing. And if you look at the Earth observation, we started using the foreign satellites at one time. We built our own Indian remote sensing satellite 1A that was launched in 1988. And currently, the latest one that we have put is a Cartosat 3 satellite, which has a spatial resolution of close to 26 centimeters, less than a feet. And somewhere in 1995, India became the owner of a satellite which was supposed to be the best civilian remote sensing satellite of the world, and commercial applications of that and commercial acquisition of data from that satellite also started. India is having a unique constellation of satellites which can look at land, water, resources, ocean, meteorology, and cartography. Gagan was an improvement of the GPS signal for navigation purposes. But assured navigation signals are being provided now with Navik, a constellation of 7 satellites. Now, these are all the programs looking at Earth. And if you see the bottom part of it, about 170 missions, satellites and launch vehicles were done over this period. And one could see a progression in the number of missions. And essentially, the maturity of the technology, the way we have developed, the learning that we had, and partnership with industry, which started right away in the 1970s, they are all responsible for this quantum jump in the number of missions. And the capability for the launch of these satellites came first through the PSLV in the mid-90s. And the capability went up when the GSLV came along with the cryogenic stage. And the GSLV Mark III is the current workhorse vehicle of India, which had even launched the Chandrayaan 2 recently. Where do we stand with respect to GSLV Mark III? If you compare the payload capacity of the vehicles available for launch in the low Earth orbit, LEO, GSLV Mark III has something around 10-ton capability. And if you look at the Ariane 5 launcher of Europe, which has done quite a number of commercial launches, it's around 21 tons. Then we get into the Proton vehicle of Russia, which is about 23 tons. The Long March 5 of China is close to 25 tons. And the Delta 4 Heavy, it's about 28 tons. In the recent past, we have seen the Falcon Heavy of SpaceX with 64 tons. And there are developments going on in the world. In US, there is a space launch system trying to have a capability of launching 130-ton to low Earth orbit. And there is a Chinese program for Long March 9, which talks about 140 tons. This is where we are with respect to the launch vehicles. Now, beyond the Earth-oriented space program, India got into in the year 2000. That was to look at moon. That was the Chandrayaan 1 mission. There were several new things to be done in this area. One, of course, is a deep space mission. And then we also had to look at the insertion of a satellite into lunar orbit and designing a satellite for surviving in the thermal environment around moon. All this happened. It was an international mission. There were 11 payloads and also instruments from India and instruments from other space agencies did an excellent job. That was the beginning of going beyond Earth. Mars Orbiter mission was another major inflection point for us. In the year 2010, we started doing that. In 2014, we orbited. Satellite is still alive. Basically a technology mission. We did it quite well. This is the new dimension. Chandrayaan 2 followed Chandrayaan 1. In the meantime, there were other exciting things. One was a re-entry of a module from space to Earth. That happened in 2007 excellently well. Very high precision in bringing it back to Earth. AstroSat was the beginning of a dedicated satellite, a multi-wavelength observatory in space to benefit the astronomy community of India and the world. And the instruments on AstroSat are state-of-the-art or even superior to what we see from other countries. We also see the PSLV launching multiple satellites. We started in 1999 with launching 2 satellites, and a couple of years ago, we had even 104 satellites launched by the PSLV. So this is where we are today, and we are now the dawn of the human space flight, which we will talk later. Can I have the next slide? India is known in the global community as a role model for space application in India, essentially starting with the vision with which we started the space program. And the way we planned our satellite systems with the users in the loop from the 70s, whether it is for configuring the INSAT system, whether it is for funding the INSAT system, whether it is for managing the INSAT system, or utilizing that for telecommunication, broadcasting, meteorology, etc. When we started the remote sensing program, the reach was far more, the whole country, central and state agencies, they were all brought into the picture to take decisions together on what we need to build and how do we make use of it. The capacity building required in each of this organization to move into the remote sensing data as a tool along with the conventional data system. Doing this as science is good, but how do we institutionalize this in the states, in the central agencies? This was the priority of the 80s, of the 90s. And then slowly started the externalization. It's not sufficient or good if ISRO alone focuses on this. It has to be in the value chain of the user departments. And they had to have institutions for doing that. It started with the forest department, with the ocean department, and then agriculture department, and there are national agencies today. So externalizing the space application has been another strategy for us. So the communication infrastructure, the data connectivity with very high rates, broadcasting, including the DTH, distant education, one of the first priorities of satellite communication. These were all possible through the INSAT satellite system. Monitoring the natural resources of diverse nature, the meteorological observations which support the India Meteorology Department, ability to look at the environment, the ability of space systems to look at the parameters that are essential to study the climate change. These all came through. Strategic services became very important, especially with the Cartosat satellites. And in the year 2001, India launched a satellite with 1 meter spatial resolution. Assured navigation signals using NAVIC is also part of that thinking process. And the NAVIC and the navigation signals provide the location-based services. Geospatial services essentially from the remote sensing satellites and the conventional data put together serve several applications. And developmental planning at the state, at the central level by all the agencies. These are all possible through this system today. Whenever there is a disaster today in India, cyclone or flood, satellite data helps in a major way. The National Remote Sensing Center at Hyderabad has a disaster support system working in tandem with the Ministry of Home Affairs and all the states. This has been there for the last 15 years in service. And here we get a synergy of data from various governmental institutions, process it, actionable information is provided in real time to all. This has been a service which India has shown can be done using the satellite system, and it is used in many other places. In this area, we are the role model. Can I have the next slide, please? This is where we are today. The world is here today. In the new space age, we see several new protagonists. The SpaceX, the famous Elon Musk, who is a role model. Jeff Bezos of Blue Origin. And then Richard Branson of Rocket Lab. Peter Beck of Rocket Lab. Richard Branson of Virgin Galactic. Now, these are all the new protagonists, new heroes who have invested their money in doing space, frontiers of space in a very major way. In 2018, the Falcon Heavy launched a payload and directed it towards Mars. The last couple of months, we have been seeing the Dragon spacecraft delivering US astronauts into the International Space Station. The Starlink with the multiple satellites in the low Earth orbit is going to revolutionize the communication. Rocket Lab has done several launches, safe, cheap access to space, and at fast rate. These are all his objectives. The moon lander being developed by the Blue Origin is expected to participate in the NASA's Artemis space program. So this is the dawn of the new space age with several startups coming into the field abroad and in India. Now, if you look at the evolution of this over the last few decades, from the bipolar world of the 1950s, 60s, world got into the multipolar dimensions. And there are geopolitical considerations of that multipolar world. But one important thing here is competition has been mostly replaced by cooperation and joint missions together. India also participated in joint spacecraft missions, Megatropics and Saral in the past. And soon with NASA, a mission for remote sensing and disaster management applications is on the anvil. Initially, there were a couple of space agencies, but today there are 72 government space agencies. And the new entrants are at the frontiers. Of the 3 Martian missions of this slot, one is from the UAE Space Agency, an entrant of 2013, which is to be noted. Now, if you look at the global space economy, the number is quite large. US dollar, 366 billion in the year 2019. This is the estimate by the Satellite Industry Association. There are also estimates which take it to almost 425 billion US dollar. But the point is, it has been growing in spite of the economic gloom all over the world. That is, space has got a major role in the current governance structures in the global system. If you look at the 366 billion US dollar and the constituents of that, the commercial ground equipment and the space-based services take almost 70% of it. And if you look at the government sector, the government budgets, like what we provide for ISRO or NASA, it is about 25%. And the balance 5% goes to the launch and the satellite services. This is the broad profile of the space economy. If you look at the number of satellites that are in the orbit, it's about 2,100 today. Only because small satellites have come to stay. Large constellations of small satellites. Technology has enabled the space agents' good performance at cheaper rates. The new technologies are also supplementing the small satellite system and even larger communication system. And also they compete. So this is especially in 5G. There was a time in the 80s when India started using the communication satellites. There were 2 kinds of utilization. One was in the golden or the diamond. Metro's traffic, if you take, satellite was supporting. But when it went to the rural areas which are not available for the communication, satellite became the main service. With 5G, now satellite becomes a backhaul service. Recently in US, the Space Force has come to stay. Space is considered the 4th dimension of war. This has been talked about for last couple of decades, and now institutions, structures are coming to stay here. Obviously, cyber threats one has to worry about. Debris created by the satellites which are in the orbit and their own small parts going at very high speeds affect the satellites which are operating. The new dimension with the small satellite system, like Starlinks, like OneWeb, operating in 550 kilometer orbit, is that one, the issues of collisions to be understood, and the second one, for astronomical observation, there could be also difficulties. So these are all the new dimensions to be handled. Space governance becomes quite important. This was quite active in the 50s, in the 60s. Now again, there are several dimensions of it being discussed, especially with the exploration of Moon, Mars, etc. So regulatory, legal, policy matters, treaties, these all get revived. So this is the new space age, and where India is around 6 or 7 in the global committee for the last 15 years. US, Russia, Europe, Japan, China, and India, followed closely by Canada, Brazil, etc. And the recent development in the country is the structural reforms in 2 areas, to get the private sector as a co-traveler, the private sector to have a major role, and also to have friendly policy framework for satellite data. I stop at this moment and hand over to the moderator.
Hello.
Yes, sir.
So, we heard Dr. Radhakrishnan's excellent talks so far. I think it is an intermission for us to ask a few questions. There were many questions on the list. I've chosen 3-4 of them. One question is from Dharmendra Kumar. What is the status of reusable space transportation? What are the plans?
Okay, globally, if you take the space shuttle was the main reusable system, essentially to use the hardware multiple times to ensure cost effectiveness. But shuttle got closed. There was a program in Russia with Buran, but did not operationalize. India got into study of reusable systems essentially for low-cost access to space. We had a technology demonstration flight in 2016 that was to understand how this winged body behave as it goes up, as it comes back. It has the complexity of a rocket as well as an aircraft during this phase. But that was only the first step. There are several more steps to be done, and there is a program on this area.
So the program is active. That is what Dharmendra Kumar could know. There is another question from Rajendran. How do we stack up with respect to China?
If you look at the different portfolios of the space, one, of course, on the launch vehicle, I talked about it, GSLV Mark III with a LEO capability of 10 tons. There is a Long March 5 with a LEO capability of 20 plus tons. And there is a program for a larger launch vehicle. In the area of human space flight, China is one country in the world which has gone steadily and fast. We are beginner in the human space flight. But where we excel is in the remote sensing satellite system. Our constellations are much versatile and also more powerful. The next aspect is on the interplanetary missions. On Moon, both have done their experiments. Chang was there, we had Chandrayaan around the same time. But if you look at Mars, China tried to piggyback with the Russians in 2010-11 period, but that system failed even before it left Earth. But they have gone with a very ambitious program now. Now we have to see where do they finally reach as far as the lander is concerned. So in the nutshell, I should say that every country has its own priorities. Every country develops its strength. And today we are coming to a world where there is going to be joint working on several missions. And of course, on applications, India is better than almost everyone.
Good, sir. There is one question from Vishal Sharma. What are the research and academic opportunities in the area of quantum-based satellite communication?
Quantum-based?
Quantum-based satellite communication.
Let us get to the next session and then...
because it's not too clear to me.
Yeah.
There is one question from Prasad. A lot of space pollution is occurring. Are we partnering with other countries to tackle this area?
Yes. In fact, that is the worry of everybody when I talked about debris and the collisions. In the orbits where the satellites are operating, there are small parts of the past space assets, of the disintegration of the satellites in orbit. Altogether, something close to 17 to 20,000 parts going at very high speed. These are man-made debris, we call it. There are also the debris likely from cosmic sources that we will talk about it later. So on the man-made debris, there is a system required for observation of these small objects. There is capability required for modeling and find out how they are going to behave when they are going to come to the atmosphere, where are they going to fall, etc., etc. The third dimension is guidelines to ensure that we don't create the debris. If it happens naturally, yes, but don't create. These are guidelines. And why these guidelines are required? Because some countries have created, shown their ability to do that. The last one is, how do we scavenge these debris? This is a very important aspect on which the technologies are looking at. And there is also a requirement to ensure that the operating satellites are clearly away from the debris. So this process goes on. So India is there everywhere. And one point I should talk about, this community conducts a test every year. They take a large object and tell the countries, you predict when, where it is going to come enter the atmosphere. India has been participating in that, and our ability to do that modeling and prediction is quite high. We are somewhere in 2, 3 in that capability side. We are slowly building up the capability on the ground for observation. There is a multi-object tracking radar in Sriharikota. Optical systems are also coming up. At least up to the 1,000-kilometer orbit, India has ability to look at the objects which are going to be closer to our remote sensing satellites.
Good. I'll ask one more question before you go to the next part of your talk. There was a question which asked, ISRO has paid a lot of attention on socio-economic values so far, but in the decade to come, will you continue to pay attention to that, or you will go for a more ambitious exploration of the solar system? What would be the priorities?
The answer will lie in the 5 E's which I am going to show.
Okay. That's why I asked this question, so that you will go to the next in a logical way. Okay. So I think we can stop here. Ashok, Kamath, you can now get back to the rest of the talk.
Yeah. If you look at the new space age, there is ample opportunity and challenge for different domains, different communities. On one side, we talk about the exploration and exploitation. Exploration of the solar system, that is the exciting science. Today, the world is going back to explore moon. And I say today, it is for the last 15 years. Renewed interest in looking at the moon. That is where the Chang came, the Japanese satellite came, Chandrayaan came, and the US is now going with the Artemis program for looking at moon. Mars has been a destination, and there are several countries now getting into the exploration of Mars. There is already a set of landers, rovers, and more are going to have, more versatile ones are going to go there. And I must just say, a few years ago, when we had the Jet Propulsion Laboratory director in Bangalore, he told we made 25 satellites which are working in the solar system. So they have large number of satellites today looking at the planets, asteroids, etc., etc. This continues. About the universe, that is a problem which everyone looks at it, the scientific community looks at it, and the space has enabled through the Hubble telescope, through the James Webb telescope, which is going to come, and even the AstroSat. They are all part of this study of the universe. Life in the universe, this is another area of study. And the study of sun itself has advanced. The heliophysics has advanced. If you look at the Parker Solar Probe, which is going to come closer to the sun in a 7 years mission period, is something which is quite unique. India has its own Aditya mission lined up. Aditya will be looking at sun from an orbit which is 1.5 million from Earth in an orbit called L1 orbit. When we get into deep space missions, when we go beyond the Earth's environment and get into or fathom into Moon, Mars, etc., the cosmic hazard become quite important for those. We also need to understand what is going to happen with the asteroid threats, etc. So this is one part of the space activity for the future. How do we exploit the resources from space? Solar power is a classic example. Now we collect solar energy. Can we have solar power satellites collecting and then beaming back to Earth? This is one area of study. The celestial resources from Moon, from Mars, etc. are interesting. They will be useful. Helium-3 from Moon, for example, is talked about as a potential source of energy. There are also precious metals which could find use here. But how do we locate them? How do we exploit them? How do we collect and bring back to Earth? So this is one area of study. And once it comes here, how do we develop the technologies required for downstream process? Here the timelines are 50 years and 100 years, but this has to happen. We talked about human being in space, human being going to Moon. Now the community is talking about habitat in space, living there for more time, going to Mars. And if you have to go to Mars and bring the person back, it talks about 1,000 days of stay in space, as against the International Space Station, where the record is about 1 year. So we need to develop a lot in terms of technology, in terms of knowledge, in terms of the psychological aspects, sociological aspects, to look at the habitat in another planet or even in outer space. So this is another dimension what is going to happen. Now for the commercial community, there is a large space enterprise. 366 mostly comprises of the space enterprise. Today we talk about space assets. Today the satellite numbers are something like 2,000 plus. But each one of the constellations that are going to be put by the communication satellite agencies are in the order of 1,000 itself, whether it is OneWeb or whether it is Starlink, etc. It's called space assets. How do we develop? How do we bring new technology into it? How do we manufacture? How do we launch? How do we operate? How do we ensure their safety? How do we upgrade them as the technology develops? So these are all aspects of it. How do we develop ground systems required to put them into orbit, operate them, and also utilize them? And there are new areas like space tourism coming up. We have the International Space Station today, and even US is looking at private sector operating the International Space Station. So there are several novel applications of that going to emerge. So this is going to be a large area where money is involved, where operational activities are involved. And then the last one is engagement. Applications of the space systems. Human well-being is one of the important priority. And the question that you asked for India too, the bedrock of the space program is going to be application of space for human well-being. Space for security is another new dimension, and the governance of space and governance using the space systems. When we come to the human well-being, the global community has collectively brought out the Sustainability Development Goals, SDGs, for 2030 with clear targets. And the satellite systems are going to be a major player in this system of SDG 2030. If you want to understand climate, it is very clear that out of the 50 plus parameters, half of them are best observed using satellite system. And the climate is going to be a major priority for the future. Today we talk about resource management, understanding about environment, etc., etc. But now we are in a world where intelligent, actionable products using the large amount of that data that we have collected, the data analytic capability that we have got, the artificial intelligence capabilities that we develop. How do we get intelligent, actionable products using the confluence of remote sensing, navigation, satellites? And how do we reach it to the people straight in their hands from the satellite using the new technology systems? There was a time, like in the computer systems, we had centralized remote sensing data collection, taking a couple of weeks to provide that data to the user, then they will take a few weeks to analyze and find out what happens. But today we have a system in a couple of minutes from the reception, that data could reach the user. This is technology where we have, but that is raw data. But how do we get intelligent processed data straight into the hands? This is going to be a new dimension for the future. Space for security, as I said, is a new dimension, whether it is for surveillance, whether it is for defense, like missile defense, or for supremacy. Now, countries are talking about this, like Space Force that has come. Every country has programs in this direction. Space governance become more important as we have close to 70 plus government agencies, almost 5,000 plus industrial firms engaged in this activity. So, if all that we talked about should happen, engineering is the backbone. If you want to go to Mars and bring resources from there, for every ton that has to come back, we should be able to put 25 tons up. So if you have to have a meaningful satellite cargo coming from Mars, then we need to have capability. Humans in the Earth should have the capability to put 150 to 200 tons to low Earth orbit. What is happening today is beyond the SpaceX. Two developments are space launch system of US and the Chinese launch system. These are going to be the two things of the future. We talked about the re-entry missions. Why it is relevant? It is in this context. The return of human and cargo are quite important. What India has done in 2007, we had the space recovery experiment, SRE, where a module was brought back to Earth from the orbit very precisely. In 2014, we had the crew module, unmanned, brought back to Earth precisely. The human spaceflight will again show us the capability to bring them safely back here. But cargo also is another aspect of it. Space robotics, it becomes very important because if you depend only on human in loop for the future explorations, there are difficulties, limitations. How do we use an optimum mix of space robotics and the human in loop for the future? This is one of the major thrusts for the future. Something that happened in the last few years globally is 15 space agencies got together, coordinated by US, to look at one roadmap to understand Moon and Mars. There is a global exploration roadmap prepared by 2018. And it gives a program of direction for the next 20 years, where there is a station in the lunar vicinity, there is a station in the deep space station near Mars, where from the robotic missions and human missions could take off. It's a direction, but there are contributions possible from all countries in this kind of a major mission. So these are all the broad level challenges in engineering for the future. Now, when we talk about the specifics of these challenges in engineering, for example, in communication, the technology has been growing at exponential rate. The enabling technologies, competing technologies have been growing very fast. So going to higher frequency bands, now we are at Ka band. How do we get more information put through the satellite system? How do we have more power transmitted by the satellite system? How do we reduce the mass of the satellite system so that we can have more economical way of doing things? The 2-ton propellant that is carried in a 6-ton satellite could be replaced if we can have electric propulsion system introduced for orbit tracing and for housekeeping. This is taking place now. This is one immediate direction in communication engineering. Now, if you look at remote sensing satellite system, rather than sending the observed data, how do we put more intelligence into the remote sensing satellite system? How do we make it more smart? The processing that we do at the user's side, how that could be done in the satellite itself so that we get actionable products straight from the satellite. This is another major direction. When it comes to the navigation satellite system specifically, what is more important is to get into higher precisions. Today we have a GPS system with 10-meter accuracy. And we found we could reduce that, we could bring down that to 2 to 3 meters by correcting the ionospheric contribution in the error budget. Now, how do we improve it? That is in the clock that we need to have. And if you look at the Navic system, we have been importing these clocks from Europe. And now there is a major development that has taken place in this country for this ultra precision, ultra stable atomic clocks. Soon they will find a place in the orbit. So this is another direction in which technology is going. On reuse, re-entry, the thermal issues associated with the re-entry when there are instruments and when there is a human being. This is something to be understood, addressed. And how do we navigate them precisely to the place where we want? This is another area. So there are several challenges. Propulsion system itself, which is the bulwark of all these launch vehicles. How do we make more efficient propulsion system? How do we make more accurate sensors for this purpose? So there are several things in the offing for engineering community. Can I have the next slide? One of the exciting area for this country, the one portfolio in which we are a new entrants, is the human space flight. If you can just compress that slide a little bit, the bottom portion could be seen. The most important part of it is we must have a safe and reliable vehicle system to carry human beings. Dr. Kota talks about transport aircrafts and the reliability, safety associated with those systems. Now here also we talk about such reliable systems, and the reliability figures for a rocket that should carry a human being is of the order of 0.99. This has to be established over years through the pedigree of the systems, the heritage of the systems, and precautions in the design, in the manufacturing, in the testing, and the preservation phase of the system. The crew members have to live there, whether it is for a week or for 100 days or even 1,000 days. The cabin environment and the life support system are required for the crew members to be there. Now, when we talk about a mission around Earth, a mission to Moon, a mission to Mars, what are the mission strategies and operations required for them? How do we ensure that the astronauts or the cosmonauts or the vyomonauts are in touch with the ground stations as they go around the Earth or in the other planet system? What happens to the human being as they travel in this environment? The bioastronautics. the psychosocial aspects of the human being. These have to be understood. The traverse becomes large, the endurance of the systems and the human being, and the habitats that we have to generate. If you have to go to Mars, there are opportune times when there can be a mission, that is once in 26 months. And it takes almost 300 days to reach there. Then you have to wait for the next opportune time to come back. So we talk about 1,000 days. How do we ensure, how do we test on the ground for human to be in such kind of habitats? So can we bring such facilities, such environment can be created in the earth? This is another area. Risk assessment and safety is quite important. They started in US when they started with the human flights, and there are standards and there are studies in this area. Astrobiology, when we talk about life in other planets, etc., this becomes quite important. And what happens to the human being as they migrate from one place to another place, this is again important. So as somebody quite nicely put it, it is easy to take a human being into space, but it is difficult to keep them safe there and bring them back. But the human being has the cognitive capability to take decisions in situ as they see new things there. Whereas a robot is easy to take and bring back, but the robot will do what it is told to do. The intelligence or the next step of actions from a stage can be taken not in real time at the moment, but maybe after some time. This is what curiosity has shown. But how do we get into the next step of bringing cognition capability into the robot? And the robotics community talk about brain-inspired robots. So how can we get into cognitive robots? So these are all the dimensions for the future. So we have 5 E's: the exploration, exploitation, engineering, enterprise, and the engagement. Now the last question which many would be thinking is in the context of the new structural reform that has come into the country, what are the opportunities for this enthusiastic space startup system? They have been there. ISRO itself was a startup. And somewhere in the 80s, several bold entrepreneurs came forward to look at equipments that are required for the applications and application services. That is where we are today. And some of them also got into building systems for the satellites and the launch vehicles. And they have made a good progress. So there is one side is production of operational rockets and the operational satellite systems in a consortium along with ISRO. This is one clear direction. The second direction is the new trend of making small satellites provide big opportunity. The students themselves have done this small satellite system. So manufacturing small satellite systems is another major opportunity. The ground systems required for utilization of the future satellites with new technologies, with novel technologies that we could develop, or the technologies that we could bring from outside, this is a major area. And providing the services, the new services, there only brain power is required to imagine what more could be done to the user actually. And we have seen in the past decade, many novel ideas coming out. Now, this is a major area. And I go back here, 70% of the space economy today is contributed by such services, ground system and the satellite services, downstream services. Now, there is an element of risk involved in this. The risk involved in a launch vehicle system is high or the highest. Then the risk involved in having satellite systems slightly less. And when it comes to the ground equipment and applications, the risk comes down. At the same time, the turnover goes up in that order actually. So one has to choose whether you require challenge, whether you require excitement, whether you require a safe turnover, where you want to be in this niche. So the spectrum is quite wide open for the new entrants. And what the government has done is opening up the door for them to get into in a major way. And ISRO is there as a catalyst, as a facilitator for the new system. Sir, here I would stop and I will hand over to you.
Thank you, Dr. Radhakrishnan, for an excellent talk. Extremely very happy to listen to you, going from one end to the other end. There are a few questions I thought, some of the questions which were there you have already answered in your talk about the applications and all, but there are a few which are important. One is ISRO planning a space station?
See, there has been a talk wanting to put a couple of human beings into an orbit around Earth for a week's time. We are entering and understanding what is involved in really doing that and how do we develop technologies required for this purpose. So one of the next step that is discussed is to enlarge the area, the time of stay, to enlarge the area available for meaningful experiment in the cabin, which obviously takes us to the concept of space station. But when we enter into this human station 5 years from now, we should be contemporary of that period, state of the art of that period. So this is the challenge in devising a system for that purpose. And with the larger end goal, what way it is going to contribute to look at Moon and Mars.
Important, yeah. The one of the key things, for decades you have paid a lot of attention to socio-economic activities of the country. So now the role of space in oil, gas, and mineral exploration for India. What is the direction you think we should look forward to?
See, when you talk about the oil exploration, the hydrocarbon, that is what people talk about. There is an institute in Dehradun, they make use of remote sensing technology. Now, let me say one thing. When you look at the remote sensing satellite systems and how they look at the Earth and the resources, they look for specific signatures that could be captured by the satellite. For the features which are underground, these are indirect inferences, whether it is soil, whether it is minerals, or whether it is hydrocarbons. But it requires several other levels of information, types of information to be brought in together to understand, to narrow down the area of search where such resources will be located. Certainly, it's an area for the future.
The question is, a satellite is at very high height. So to go explore down the Earth, I thought that still there are a lot of technological challenges which cannot be done by itself. Is it correct to think that satellite technology by itself will not help us in exploring underground minerals or oil or anything?
It's a good question. We never believed in that actually. Now, if you look at the resources management system, natural resource management system using satellites, there is a clear requirement of the ground information or collateral information. Depending upon the resource theme that we are looking at, the level of ground information will be varying. If you look at, for example, on one side, water can be observed very easily using a satellite system. If you look at the agriculture, if you look at the vegetation, we can look at it, what is on the surface. When you go to the next dimension of trying to understand the soil, the moisture in the soil, which is up to a few centimeters, it is a difficult issue. But what satellite can give is some of the physiographic features and stratification of the physiography. Within that, we must have large number of ground truth studies. Then only one can categorize the soil into X, Y, etc., etc. When you get into minerals, it becomes more important. There are features. Synoptically can be seen like a fault line. If you go for a conventional survey in a small area, you may not be able to see that. But satellite could pick up those synoptic features. That is the case for water targeting. Groundwater targeting also requires this kind of information. But there is a large amount of ground truth required for understanding. So I would say in some case, it may be vary from about 95% for certain features to about 20 to 30% in the other area. If you look at the forest, for example, if you want to understand the forest density, a satellite can do that. But if you want to make a working plan for the satellite, it can do only limited purpose. The rest of it is on the ground, but it helps.
It helps. It can be aid to the.
Aid to that.
It is an aid.
Yeah.
The other 2-3 questions were there on the space arms race. They were asking, look, China is moving forward in that direction to use space as a means for arms control or control. Can India remain without doing anything in that direction?
See, there are a couple of things, and I will be quite conservative in addressing this issue. If you look at the remote sensing satellites with resolutions of 1 meter or even better, they will be able to see several things happening, not only in our country, but elsewhere. And there is an open sky policy globally. That is, we can look at what is happening around the world without prejudice to their security aspects. So this is one area of high resolution satellite systems for surveillance. The other area, of course, are like defense, missile defense system, etc. need to be developed. The third part of it is communication specifically. I would say GSAT-7 satellite was a dedicated communication system with the footprint over the seas. So there are things happening in the country.
But as a space command, the question is, are we planning a space command to look at the space as a means to have supremacy?
I may not be the right person to answer that question, but there is a Defense Space Agency. It should be.
A lot of those questions were there. So I thought I better ask. But there is one question, is the satellite being jammed by another satellite? A lot of questions were in that direction. What are the possibilities? At all, there are possibilities.
See, there is a question of the security of the space assets now. If you are using satellite systems for our daily working, whether it is in civilian or in military domain, security of these assets become important, whether it is electronically destroyed or physically destroyed. So there are dimensions of study in this area. And when you talk about the subject that we just now discussed, this is one of the major concerns there.
That is the major area.
Yeah, it's a major area.
We still have to find a way to handle that. There is one question they were asking. In the world over, are there any plans for governing space traffic control? Because so many satellites are now going around. Is there any UN or anybody planning something like a space traffic control?
There is an agency under the UN system, which is the International Telecommunication Union, ITU, which has the member states as well as several space actors coming there as observers. So if you have to put a communication satellite in a geostationary orbit, which is considered as a resource in space, it has to be allocated. And there are regulations and there are procedures how to get that slot, how to preserve that slot, and what are the disciplines to be maintained when you beam from that location. So this is done by ITU, International Telecommunication Union. For all the satellites that are required to be put in the orbit, what frequencies have to be used, what power levels have to be used, etc., etc. These are also coordinated and cleared. This is the agency. But the new dimension is going to come with the space debris, creation of space debris, or use of nuclear systems in the spacecrafts. On one side, you require nuclear devices for powering the deep space missions. But if that mission does not leave the Earth and comes back, what are the damages, etc.? So these are all the things discussed at the UN level. There is a UN Committee on Peaceful Use of Outer Space, where the common concerns are discussed. Now they talk about the long-term sustainability of the space assets. This is one topic being discussed.
Coming back to the work that was already done by ISRO, when will NAVIC be available for public use in a big way?
Yeah, there are several attempts for the ground systems, the receivers that we need to carry. I'm sure that soon it is going to happen, the device which can take the signal from NAVIC as well as the other systems. And I see a lot of developments taking place now in this area.
Maybe you need an antenna which can integrate all those systems.
And a small handheld device for that.
Handheld device, so that it becomes commonplace.
Yes.
Because the satellite system is operational, but now we have to exploit it by enough groundwork that needs to be done.
Absolutely.
That is perhaps what is required. The other question that was asked was opportunities for satellite ecosystem for firms. You have addressed this point, but maybe it is worth telling a little more in detail. A lot of firms want to make small satellites. What are the opportunities for them? Can it be a viable business?
Yeah, as I said, when you talk about viability, when you talk about the risk involved, when you talk about the facilities or the expertise required, these are all the dimensions to be looked at actually. So on one end, there is providing the space-based services, new services. Now, if you look at the last decade, you have got several novel ways of providing service to the people, which we never thought about in the past.
Yeah.
So with the satellite system and the data that we have got, many actionable products could be taken. This is one area which you require a small office and a good brain and a good reach. When you talk about the ground equipment required for the newer satellite systems to be used in a larger way, and when we talk about handheld devices which collect the smart data coming from the satellite straight for your use, like your mobile now, this requires novel equipment, ground systems to be made. And this is one fertile area for the engineering community to get into. Develop some of them here, absolutely possible, because we have got nice ideas, or tie up with someone for that purpose. But I would always advocate self-reliance and creation of the intellectual property here itself, so that it is not only marketed within India, but you have to have a global market in picture for it. That is important. When you talk about satellite systems, especially, it becomes easy today. And there are people saying that from a supermarket, you can go and buy a small satellite today. That is the level to which things are happening. So one concept is for science, for Earth observation, experiments, small satellites will play a major role because the risk is small. There is a small satellite, you bring a new technology, test it, and then make use of it, larger than committing a larger system. So this is one area for specific applications. And if you look at the satellites that ISRO has launched, almost 80% of them are of that class, done by students, community from various places. So this is one area where we could get into. There are also the flyby configurations, replacing a larger satellite with many small satellites, taking out a bad satellite and then replacing it, or bringing a new technology there to try. So this is another concept. If you look at OneWeb and Starlink, it's a new concept of 1,000+ satellite constellation taking place. What is the opportunity? Can we manufacture them? This is possible. So blind manufacturing of whatever they have devised or intelligent configuration of small satellite system. These are two areas where we can get in. And what is required is a good laboratory, a clean environment, and testing facilities. And you need not have everything in-house. And certainly agencies like ISRO and other places could be made use of this purpose, provided time is available for that. Launch vehicle, now one trend in communication is to go for heavier satellite system, or even for the exploration, you require much, much heavier satellite. But for the launch of the small satellite system in thousands, there is a niche for small satellite launchers. PSLV had a niche. Vega was part of it. There were a couple of launch vehicles of that class, 500 to 1,500 kilogram could be put in a lower orbit. But with the new concept, there is a market for even launching large number of satellites, 500 kilogram and less. So this is another area one could get into, but there is an attendant risk involved in this process and attendant non-availability of the technology, because this is a guarded technology for a launch vehicle. So one is able to get through. It's a very exciting field. It's a thrilling field to have a rocket system, but it has to be with the economics associated with that. And today, obviously, there are some 20+ such small rocket launchers being developed by several agencies. So you have to compete in a market.
The question in the minds of many of the industries is, today normally we think that if private industry today, you are trying to bring in private industry in launch vehicles, satellites and all, but can a private industry make it as cost effective as today ISRO is able to? There is a doubt on that.
Yeah, see, if you take the global situation, many of the space systems are subsidized.
That is the point.
In communication satellite, it is basically guided by a replacement of terrestrial systems, and their cost effectiveness is important. They compete. When it comes to the remote sensing data from the satellite, NASA tried that in the 80s, but they decided remote sensing data will be a public good, especially when it comes to the meteorology observations for climate, etc., etc., etc. Only for infrastructure planning services, it is mostly commercial. When it comes to the launch system, even for Arianespace, I understand that there is a backing from the government. It is not the total cost plus the margin that is charged to the user here. So new models have to develop in this area.
So in India, when you are now asking private industry to do the launch vehicles, there has to be a model whereby it becomes viable.
Yeah, it is, for example, there may be many of the high cost facilities which are required for this purpose, which will contribute to the cost. What can be done for that? Can it be provided as a common service? This is something to be understood.
I think that this policy needs to be evolved for this industry to become viable.
Yeah.
Quite a few students have asked this question. How can they get to know about the current research going on in space-related field? How the information can, and how could they get into it?
See, if you look at the public communication in this area, there are quite a few sites where you can look at it. Space Reference, for example, talks about what is happening in the area of space sciences, etc., etc. If you look at the space news, under the missions, under the commercial activity, the legal activity, what is happening, you get up-to-date news. These are sites one could access. And generally, it is comprehensive and it is non-political. I would say they give all the information. And there are subject-wise areas also. For example, if you talk about planetary exploration, what is happening there could be seen very specifically. They do detailed study in those areas. So today, if you look at the web, there is plenty of information available from these areas.
Good. I think perhaps one need to, maybe if there is one or two agencies who can collate them together, bring them together, and then make it available to the university system. Possibly the university system can engage itself in a much bigger way, in a more productive way.
Absolutely. I must also add at this point of time, this has been one of the thrust areas for ISRO too. We have done it in different ways. One way is to bring such subjects into the curriculum and the high school and +2 stages. You will find today in geography or in geology or in physics, etc., areas related to the space written there. They start about 30 years ago, I would say. Today, there are specific programs run by ISRO to bring the new generation into the picture. There is also a big initiative in ISRO in the last couple of years to bring them to look at this launch itself. There is a stadium in Sriharikota where at least 10,000 people could come and watch. Then that excitement, that inspiration that it provides is something new. But the question of having an organized system of information dissemination is something which one has to think of.
Really
NASA has an
have to
excellent
address.
system for this. NASA has a very well developed system for public communication and also public outreach and also enthusing the community. For example, when they went to the mission Moon, Artemis, they started well orchestrating the global community to say that yes, we all should go into Moon. These are all programs directed towards that.
Yeah.
This is important.
So thank you very much. I must tell you once, long back, I was in University of Hyderabad when I requested your predecessor, Dr. Kasturangan, that there is a need for university and ISRO to come together. He arranged a meeting where all the directors of the ISRO centers came to University of Hyderabad. I don't know whether you remember. Then we found non-science and technology based, some 20 projects were given to social science group. In the university, only one university, ISRO gave 20 projects. It shows there are a lot of opportunities. We need to see how to expand this opportunity.
I may just add, one should not feel that space is only for the scientists and the...
that is the point.
See, for example, space commerce has become a big subject. The space law is a very major subject today. And the social aspects, the cost benefits coming from the space systems is another major area. And if you look at even the human space flight, there's a lot required to be studied for the psychologists getting into that area. So it is research in jokingly A to Z, agriculture to zoology are relevant.
I think maybe greater engagement, as you rightly said, is required so that a greater participation from researchers, students can occur, and the community as a whole, the youth community can get benefit by that, and the country in turn can get benefit by that.
Absolutely. Absolutely.
So, thank you very much, sir, for a wonderful talk and wonderful way of explaining all the things. Lots of questions you were able to answer. Now I'm giving back to Sushila.
Thank you very much, Dr. Radhakrishnan and Dr. Kota Harinarayana. I think for as long as human memory goes, we've been fascinated with what's out there in many different ways. And today you've talked us through how India entered the space age in 1962 and then took us, step by step through to where we are now. You helped us understand about Earth-oriented research and exploration to actually now looking outwards and looking at space and deep space in a big way. And I think you've excited all of us by talking about the new frontier for India, which is manned space missions. Everyone is excited about that. Just a few takeaways from today's talk. You talked about the fact that India chose to invest in what is clearly a high-risk sector, but that sector has given us great dividends through the years in the way technology has evolved in the kind of ecosystem that we've been able to build and so on. We also learned that one of the most important things about undertaking a high risk undertaking such as this is that we have to learn to build resilience. And that, you said, has been the cornerstone of our space programs. We can be justifiably proud of our achievements. And you talked about the fact that we are global leaders in the application of our space projects. And while this is clearly a global initiative and it does require international cooperation, and that is the way we are headed, but still the fact that we have learned and have understood how to harness the power of space technology for greater social good is something that we have to be proud of. You mentioned that this was all possible because of the fact that users were involved at every stage, right from concept through to implementation. And I've heard you say this before as well, multiple times, why that involvement is so important. And this is a critical learning, not just for space, but for anything that we undertake. And I just want to highlight that. You also talked about the need for close coordination. This is so complex, and the need for coordination between many government and private agencies just to get things done and then keep it going on an ongoing basis. It's not something that you just do one time. But while all this is exciting, you highlighted 2 points where there is a lot of work that needs to be done, and those are space debris and security. And clearly those are areas that are taking a lot of mindset and will need to be addressed. Not just by India, but by everyone who's in the space, in space exploration or space exploitation. And then you took us into the exciting new space age and talked about the 5 E's. A few important things there. You said there is a need for precision and precaution at every step in every aspect of what we do in that area. You talked in detail about engineering is required and so on, but also so many other disciplines. So this is so deeply interdisciplinary, and many questions were asked about how I'm in such and such space. What can I do to contribute to the space program that India has? And I think you gave us the answer by talking about things like bioastronautics, psychology and sociology, and social impact of all of this, law, commerce, so many different areas, so many different skills that need to come and have a bearing on the success of our space programs. You talked, I think one very important aspect is the success of ISRO's space programs has been possible only because of the participation of many entrepreneurs, again, in all stages of the program. And you've left us with many questions that are open and exciting issues that many of us, many companies, startups, and so on, can pick up and find answers to. So I think this has been a very energizing session, and I really want to thank you for the time that you've taken to be with us. Dr. Kota, it's not easy to moderate when you have 100+ questions thrown at you, and you've done that brilliantly. With the background that you have and the close relationship that both of you enjoy, that this conversation came out so enjoyably for all of us. So thank you very much, and our participants, 100+ questions shows us the level of interest there is in this space, and we wish you the best. And next week, the same time, we will have our next webinar. This webinar is being recorded and will be put up on our YouTube channel by Monday. Please look for it there, and please do keep joining us week after week. Thank you very much.